Hello everyone, welcome back to the channel. Today we are going to solve this question called make them equal from Codeforces. So it is very interesting question and I felt very good after solving it. So let us take a look at the question. So you have an array of integers a of size n. Initially all elements of the array are equal to 1. You can perform the following operation. Choose two integers I and x such that x is greater than 0 and I is basically between 1 and n, both inclusive, and then increase the value of ai by floor of ai by x. So uh, this is indirectly or directly, you can say, making ai is equal to ai plus ai divided by x, means this is integer division. And after performing all operations you will receive ci coins for all such I that ai is equal to bi. Okay, so your task is to determine the maximum number of coins that you can receive by performing no more than k operations. So our constraints are like size of arrays given, which are b and c, will be less than or equal to 10 to the power of 3, and our k means the number of operations we can perform is less than or equal to 10 to the power of 6. So yes, basically that's the format of input, and for output we have to print the integer, which is the maximum number of coins that we will get after performing no more than k operations. So basically, first intuition in our mind comes that uh, let's try to find some pattern to make the given values in b. So yes. Okay, so let us take a look. Suppose one value from A array, all the values from A array are basically 1 in the beginning. So suppose uh, entries in the array B, so what are the constraints on it? So it can be maximum of 10 to the power of 3. So it can go from 1 to 10 to the power of 3. Okay, so suppose if I have to make 1 from this any of the 1 that is present in ai, so I don't have to perform any operation, right? So it will be 0. It will be 0. What about 2? What about making 2? So uh, one thing I can notice is that I must perform this thing. First operation, my first operation is going to be taking x as 1. Okay, so otherwise 1 plus 1 divided by x, this is going to be my first operation. If x is not 1, then this resulting value will be 0, so it won't make any impact or change our value. So for first operation my x is going to be 1. So that's not much important in our solution, but just an observation. So to make 2 we have to perform one operation on 1, like choose x equal to 1 for that. To make 3, what we can do is that uh, take this value, first make 2 from the given ones and given ones in the array of A, then choose x as 2. Okay, so it is going to be 3. Okay, so to make 3, minimum of 2 operations are required. Okay, to make 4, minimum of 2 operations are required. Why 2? Because I can directly choose from here, I can choose x as 1, right? So it will be 4. So I can achieve 4 in the minimum of 2 operations. So when you try to plot this pattern, you do not explicitly find any nice pattern which can help us in solution, but we can take help of these constraints which are not too high, right? Basically you can write O of n square or O of n square log n solution, right? based on the given constraints. So we'll try to take leverage of that. So what we will try to do is that we'll just brute force all the values and check what is the minimum number of operations that we can achieve to make any given number. So suppose I have to uh, make 7. Suppose I have to make 7, then from what integers can I make 7? I can make it, let's suppose 1 2 3 4 5 6 and 7. Okay, so to make 7, okay, not 7 exactly. Now I can try making 7 directly from 1. So can I make 7 directly from 1? 1 by 1. This is the only one operation that I can do, means only one x that I can choose if my AI is 1. So it is going to be 2. So it is not possible. So let us try from 2. So 2 plus 1 by, oh sorry, 2 by 1 is equal to, it is going to be 4. So this is not possible, and one more possibility for 2 is that we'll take excess 2, right? So it will give us 3. So in this case as well, it is not giving us 7. So we can check it for 3 as well. So it will be like 3 plus 1, and so let's do it explicitly. For 3 plus 3 by 1, it will be 6. So this is also not giving us 7. So I can do 3 plus 3 by 2, it will give me 4. Yeah, 4. This is also not giving us 7. And 3 plus 3 by 3, so this will also give me 4. So this is also not giving me 7. So basically I'll check till that value minus 1, means for 7 I will check for all the integers. Sorry for the disturbance. So where were we? So we will try to brute force for the all of the values which are less than that number. So what number gives us the minimum value, minimum number of operations to get to that number? So we will try to do that, and it will take O of n square, right? So basically it will take O of n square, and which can fit our time limit constraint. And then we have our number of operations needed to get any of the values from 1 to 100, 1 to 1000, right? So we will pre-compute that in our code. And what after that? So this is the most interesting part of the question and the solution as well. So see, so what you have now. So you have some cost. Okay, so you have some cost to make given number, and then you have some reward reward which you get if you make that number, if you make that number. So is it reminding of you something? Is it reminding you of something? So it is basically a classical knapsack problem. You know what classical knapsack problem is? So it is basically a DP problem, so dynamic programming problem, where it is framed that some objects will be there, their weights will be there, W1, W2, W3, W4, and so on up to Wn, you can say. And their costs will be there, costs or values, you can say v1, v2 corresponding values will be there. And you will have one knapsack, so some storage that you have with you, and it has a capacity at most of w. Okay, it has capacity at most of w, and then you want to maximize the value, maximize the value that you can take in your knapsack if you have this constraint that your knapsack cannot hold weight more than w. Okay, so it can hold w, but it must not hold greater than that, greater than that. Okay, so this is basically the classical knapsack problem. So where uh, your WIs can be modeled as cost to make a given number, and your values can be modeled as reward. Okay, so that was the whole uh, solution. So I like this problem because it has mixed concepts, and I felt really nice after solving this on my own. So let us head toward the solution. So if you don't know how knapsack problems are solved, so you can watch some tutorial for that, or I will be uploading a tutorial for that in some days. So I should have uploaded that first, and then should have uploaded this video. But anyways, so I'll upload that knapsack's problem solution as well. So I'll give you brief overview of what knapsack and what its solution looks like. So let's head towards the code. And one more thing, so for knapsack, okay, so for knapsack, for those of you don't know, uh, the complexity of that is O of n into w. Okay, so number of items you can take, and w is the maximum weight. This is the max weight that your knapsack can hold, and this is number of items. Okay, so now you will be wondering, our n is 10 to the power of 3 and our w is of 10 to the power of 6, because uh, our k is basically up to 10 to the power of 6, so it is going to be O of 10 to the power of 9. So it is not gonna fit our 2 seconds time limit. Okay, it is not gonna fit our 2 seconds time limit. Okay, so another trick here is that, suppose what can be the maximum number of operations you need to do to get maximum value. Okay, so to get 1000, after printing the values which were pre-computed, I noticed that to make 1000 you will need at most of 12 operations, and to make 999 you'll need something like 13 or 12, but 13 is the maximum operations that you need. Okay, so what I can infer is that if every value is 1000 or 999, so every index takes 13 operations, and if my k is greater than or equal to n into 13, okay, if it is greater than or equal to n into 13, then I can make every one in the array A to value equal to uh, any of the value in the array B, right? Any value in the array B. So what I can infer is that when k is greater than or equal to n into 13, I can just give it my answer, give or output my answer as sum of all the ci's. Okay, because I can make every item which is there in B starting from this one in A, if my k is greater than or equal to 13, so, n into 13. So I will show that to you as well. So see here. Here, this is the pre-computation that is involved. So this is the array that will store the minimum number of operations needed to make that element from starting from one, and this here, let's run this. suppose number of test cases n and k. So starting from here, you can see that for 1000, okay, for 1000, okay, maximum is 12. Okay, wait. So yes, so maximum is 12. Wait. So yes, maximum number of operations you need to get any element from 1 to 1000 is basically 12. So you can print these values, pre-computed values, to get understanding of that. And now you know why we can write the knapsack solution, right? So basically I can write O of n into uh, what you can say, O of n into 13n, right? 13n. So this will be the value of k, the maximum value of k that can be, that should be solved by our knapsack, right? So it will be O of 13n square. So basically O of n square. So this is our memory complexity, and time complexity will be O of n square only. So yes, that was it. And talking about knapsack problem, so initializing this dp state to -1, and then calling this solve function which performs our calculations. So I'll tell you briefly what this solve function does. So if index is greater than or equal to n, it returns 0. So basically dp of I comma j here, dp of I comma j represents that how much, what you can say, how much maximum value can I make, how much maximum value can I make, if I start picking, if I start picking items or objects starting from ith index and initial capacity of j. Okay, so this is basically dp of I comma j denotes. And yes, so if it is already calculated, we just return that and initialize our answer to L long min and call maximum of answer comma this thing. So this basically signifies, so I will not take the current item. Okay, so I will not take the current item and go forward, and this transition signifies that I will take the current item and then go forward. And when will I take the this item? Only when I can take this. So my capacity of knapsack doesn't gets broken, right? So v of index dot second, so adding that value plus calling solve of index plus 1, so starting from the next index, and now my weight will be decreased by v of indices dot first. So that is basically the idea of dp. And finally memoizing the answer in dp of index comma weight. So for further calls it will be good. So finally returning the answer. So that is basically the code. Hope you enjoy solving the problem and listening to the solution as well. And yes, so here if I try, let's try, why did I try 13 here, I don't really remember. So let us try if it passes by doing it 12 as well. So where is it? Okay. So it should pass. Yes, it nicely does. So that was for this video. Hope you enjoyed solving the question and listening to the solution as well. So this was a really nice problem and I enjoyed solving it so much. So I thought sharing it with all of you. So for more such interesting competitive programming problems and solutions related to those, stay tuned with our channel. Consider liking the video and staying subscribed to the channel. Hope I see you again watching my videos.